All right, so what I want to start off with today is doing a simulation again to help us understand the content. The content we want to understand using simulation is the idea of a confidence interval to start off with today. And hopefully we'll also understand hypothesis testing. We will introduce hypothesis testing today. So let's start simple. Let's, again, assume we're in a situation where the population standard deviation is known. So we're going to do in general, 100 times 1 minus alpha percent confidence interval, CI, to estimate something, to estimate a population mean mu. Most commonly, the percentage people use is 95%. That's the most common percent to use. It's not like you have to use 95%. It's just the most common thing people use. People are kind of stuck on it. You should be able to deal with 99% or 90% or even 98.7% theoretically. If this is 95%, that means 1 minus alpha is 0.95. And so alpha itself is 0.05. Alpha is called the level of significance. The entire thing here is called the confidence level. Confidence level. And alpha itself is called the level of significance. Alpha itself has more meaning in the context of hypothesis testing, which again, we're going to start talking about hypothesis testing today. As you know, what does a level of significance really represent? We're trying to estimate a population mean mu, and the simplest case is to go ahead and assuming that the population standard deviation sigma, and therefore also the variance sigma squared, is known. Okay, it's just a simpler calculation in that setting because we don't have to worry about the t-distribution. It's not really realistic in most real-life applications because in real-life applications, if you don't know mu, why would you know sigma? Right? In most real-life applications, you wouldn't know either one. But to keep things simple, we go ahead and at first assume we know sigma. And the formula written with capital X bar instead of lowercase x bar is really a formula involving random samples, a statistic that is a random variable. It's got a distribution. X bar is a point estimator, right? Our favorite point estimator. It's a statistic. It can be computed from a random sample, but a random sample in the abstract is just a list of random variables and random variables with the same distribution. And so this has got a distribution as well. That's important. It's sometimes called a sampling distribution. I haven't really emphasized that as much as I should have. It's often called a sampling distribution. It's a point estimator. It's unbiased, right? Expected value of x bar is mu. The mean of the mean is the mean. That's a big, big deal. Okay. Fundamental thing to know out of statistics. But we want to widen it to an interval estimator called a confidence interval. We need a margin of error. Dr. Wetzel usually calls it capital E for error. Some books call it M for margin of error, or maybe MOE for margin of error, MO. Okay, it doesn't matter. I wrote it as a capital E there as if it's a random variable, and that is the case in the case where sigma is not known, and you have to use S, the sample standard deviation. But when we know sigma, it's actually not a random variable. Maybe I should have used a lowercase e. The formula for that margin of error is z sub alpha over 2 times sigma over square root of n. Sigma over square root of n, by the way, is the standard deviation of x bar. You could call that sigma sub x bar. square root of the variance of X bar. You might remember, I hope you remember back in chapter 7, we had a formula for the variance of X bar to be sigma squared over N. And we're taking the square root of that. This has got a name. It's sometimes called the standard error. Standard error. Actually, the name standard error is inconsistently applied sometimes. Here, the standard error, I'm using this name to represent the standard deviation of X bar, meaning standard deviation of its sampling distribution. However, the word standard error sometimes applies even when you use S instead of sigma, even when you use a statistic here instead of a parameter. You get the distinction? Sigma is a parameter. It's a fixed but unknown, perhaps unknown number. We're pretending we know it now. N is a fixed sample size. This is a number. If I use an S there instead of a sigma, a capital S, say, then it becomes a statistic. And it's just an estimator for this thing. As usual, when the subscript there is for the Z, that subscript represents the area to the right of that Z value. If this is a standard normal distribution right here, N01, then Z sub alpha over 2 is the number along the axis so that the area under the curve to the right of that number is alpha over 2. That shaded area is alpha over 2. So again, in the most common case where alpha is 0.05, if alpha is 0.05, that means alpha over 2 is 0.025. And Z sub 0.025 is a number you should probably remember until the day you die, is 1.96 approximately. Right? If you do statistics every day, you should remember that for the rest of your life. Confirmation. Go to the distribution menu on your calculator, go to inv norm. Area 0.975, that's a CDF value, and area to the left, if I want the area to the right to be 0.025. 1.96, very close. But if you had some other value of alpha, then you'd get a different number. Let's try to understand this via simulation now. Let's say we're simulating from a uniform distribution. We simulate sampling from a uniform distribution on the interval from 0 to 10, like we did before. With this, we'll go ahead and use a spreadsheet to keep it simple. If we assume the spreadsheet's random number generator is good, then we're essentially pretending we know the exact mean and the exact standard deviation, in fact. Mu would be 5, right? Halfway between the endpoints. What's the variance? Sigma squared. Look in the table. For uniform distribution, it's b minus a squared over 12. You could confirm that by integration. I mean, the 12 seems kind of mysterious. Why is it a 12? That's just the way it turns out. You can confirm it by integration. So in this case, that's going to be 10 squared over 12, 100 over 12, which you could also reduce if you like to 25 thirds. Oh, that'd be 8.3 repeating. And then the standard deviation is going to be the square root of that, which will be a little less than 3. Oops. 25 over 3, up 8.3 repeating. Take the square root of that. About 2.887. Let's round it to that. 2.887. So we're pretending we know effectively what sigma is here. What do I want to do the simulation to help us understand this? I want to use rand on the spreadsheet to get random samples from this distribution. Sample with a certain size n. What should I use for n? I could use anything I want. Let's make it not be too big. So I'm not copying and pasting way down the spreadsheet. Maybe n is 10 or something. And we'll compute this interval and see if it captures the true mean or not. Let's do a 95% interval. If I do that, the idea is it should capture the true mean about 95% of the time. Let's see if that holds. It's probably going to be easier, actually, in this case, if I do the random sampling across the rows instead of columns, because I'm going to want to calculate the x bars and the confidence intervals and be able to go down various rows to see whether they capture mu or not. So 10 times rand is what I can use. That big enough? You guys in back? Okay. And don't be bothered by the fact that the numbers change all the time. Random samples of size 10, say, n is 10. A, B, C, D, E, F, G, H, I, J. Go to column J here. I memorized that E is the 5th letter in the alphabet, but I haven't memorized that J is the 10th. I should do that from now on. Okay. There's a random sample of size 10 from the U010 distribution. What's the mean? Again, it changes all the time. That time it's 5.76. That's a point estimate. That's an observed value of the point estimator. It's a little x bar, an observed value of capital X bar. And we can do that over and over again. So this is a random sample of size 10, but let's do this sampling, 100 times. So I got 100 samples of size 10. Here we go. Those are the point estimates. Let's widen these to interval estimates. A left endpoint and a right endpoint. Okay. Observed value. I use the actual observed value of x bar. Minus 1.96. I'm doing a 95% confidence interval here. Times sigma was the square root of 8.3 repeating. That was the 2.887 divided by square root of n. N is 10. That'll be the left endpoint. The right endpoint will be something similar, except with the plus sign, right? Sigma again is about 2.887. Divide by square root of 10. Okay, this particular interval, 3.67 to 7.25, is capturing the true mean 5. It is centered at 5.46. Can I calculate? I hope. Wait a minute, that doesn't look right. What did I do wrong? Or is it right? Maybe okay. I'm just double checking the margin of error is the same on either side. So 7.25 minus 7.25 minus 5.46 is what I'm doing on my calculator right now. Gives 1.79, and 5.46 minus 3.67 is also 1.79. Okay. Margin of error for this particular one is 1.79. In fact, because sigma I'm pretending is known to be 2.887, the margin of error here is not going to change, but X bar does change. So the interval changes. If we don't know sigma though, and we got to use S, then the margin of error can even change. Copy and paste these down. Since these are 95% confidence intervals, about 95% of them should contain 5, and 5% will not. There's one that does not. Maybe there's a fancy way to use COUNTIF to count the number that do not, but I'm not quite sure how. Let's see if I can just visually do it. There's one. I'm probably going too fast. There's a second one. I got to look at both columns. That's the hard part here. Oh, almost there, but not quite. Oops. I don't know what happened there. There's a third one. Oh, sorry. My scrolling is not doing so hot here. So we're up to 3 of them that do not contain 5. I think, oh, there's a 4th one, just barely. There's a 5th one right there. Is it going to be exactly 5? Not necessarily, right? Because they're simulation, randomness. There's a 6th one. So it looks like 94% of them contain 5 in this case, and 6% did not. It's all approximations, right? Because of randomness. That's the idea behind the confidence level. When you do the simulation, 95% approximately will contain mu. Can the 95% be interpreted as a probability? Yes and no. You could interpret the 95% confidence level as a probability if you are thinking about it before the fact. I am about to do some random sampling and compute a confidence interval, and I would like it to be a 95% confidence interval, and I'm wondering before the fact, what are the chances that it will contain mu? If you're doing a 95% confidence interval, you would say the probability is 0.95. But when you actually do the interval, when you gather the sample and compute it, get an interval, and you look at that interval and say, what are the chances that that mu's in there? You can't really assign a probability to that. I mean, if somebody knows mu and you want to talk about betting odds, I mean, effectively, you could sort of think of it as a probability, but once you've done the sampling, all the randomness is gone. Probability is about randomness before the fact. So we usually avoid thinking of the confidence level as a probability. We interpret it as, well, a level of confidence. I'm 95% confident in this interval. I'm pretty sure. But since we're always thinking about it after the fact, we don't typically think of it as a probability. But if you do simulation, if you imagine doing random sampling from the same population with the same sample size over and over and over again, you could say about 95% of the intervals will contain mu and 5% will not. But you never know which ones do and which ones don't. Yeah, right? I'm pretending I know the population here. I'm assuming this is an accurate simulator with RAND. I'm pretending I know the true mean is 5. Is it really random though? Is the spreadsheet really random? That's not what you mean. Some people call technology things like this on spreadsheets pseudo-random. Because technically speaking, they are generating their numbers by non-random processes, and if you want to be technical about it, but it simulates randomness. And so you can never quite be sure that it's quote unquote perfect or even necessarily close to perfect. It's usually good enough though if it's pretty good, and I guess we trust it, basically. Can I clarify anything there? What if we had used the sample standard deviation in each case. (100) times 1 minus alpha % confidence interval to estimate mu. Sometimes you just say for mu, but in reality, it's to estimate mu when you're in the more realistic situation where sigma is unknown. Then the formula is x bar, notice it's capital, plus or minus t sub alpha over 2 times capital S over square root of n. That's capital S. Both the point estimator in the center of the interval and the margin of error are random variables. Statistics that can be computed from a random sample and therefore are random variables. X bar has a distribution. By the central limit theorem, it's approximately normal, even if your population is not normal, as long as n is large enough. S has a distribution. Is S's distribution normal? Can't be exactly normal, because S can't be negative. Could it be approximately normal? Maybe. N is large enough again. Is there a central limit theorem for S? We won't get into that at the moment. Where you compute the t-value based on a certain number of degrees of freedom, which, sometimes we call little gamma. Sometimes I call it df for degrees of freedom. It's n minus 1. That's the degrees of freedom. Is degrees of freedom always n minus 1 in statistics? No, it's not. Some people think it is, because that's the most common thing to use. In statistics, degrees of freedom is not always n minus 1. Chapter 10, we'll see examples where it's not. Chapter 11, we'll see examples where it's not. Second most common thing to use is n minus 2. It depends on the situation, okay? There are situations where it's n minus 3 or n minus 4 or n minus 5, or in chapter 10, actually, something even more complicated. Something that involves the most unpleasant formula in statistics called the Smith-Satterthwaite formula that I've hardly ever computed by hand, because it's almost impossible to use without making a mistake. You could look it up, Smith-Satterthwaite formula. DF is not always n minus 1, but in this context, it is n minus 1. Sample size minus 1. Use a t distribution with n minus 1 degrees of freedom. A t distribution has a PDF, a density that looks like a normal distribution. It's bell-shaped. Looks like a standard normal. It's centered at 0. However, it's not a normal distribution. The formula for its PDF is different. A normal distribution, the PDF formula involves e to a power. Looking in chapter 7 and fixing the typos, you see a t distribution does not involve e. I could call that a capital T sub n minus 1 distribution. What's different about it, how compared to a normal? It's a bit more, besides having a different formula, it's a bit more spread out. Its mean is 0, but its standard deviation is bigger than 1. It's not standard normal. And it's got heavier tails than a normal distribution does. If you graphed a normal distribution on the same scale, the standard normal distribution, it would be a little taller and less spread out. This would be maybe a standard normal distribution in the same picture here. However, as n gets larger, the black and the red curves get closer and closer together. As the degrees of freedom gets larger, the black curve looks more and more like a normal curve. You could say in the limit, as n goes to infinity, they merge. They approach each other. So when n is large, you can kind of get away with using a normal distribution. if you really wanted to, and it would be give you approximately the same answer. So again, let's use the calculator to find t sub alpha over 2, for example, if alpha is 0.05, so alpha over 2 is 0.025, and we're after little t sub 0.025 related to our simulation, and is 10 for our simulation. So if we use degrees of freedom to be 9, what will we get here? Need inv t. And area 0.975, degrees of freedom is 9. Should be a bit bigger than 1.96. 2.262. So I'm about to use this formula here on the spreadsheet with that value of t, 2.262. But remember, s is still a random variable. The different samples of size 10 will have different observed values of s that I could call little s in each case. So again, not only is the point estimate going to be a random variable, but the margin of error is going to be a random variable in this case. I'm more justified in calling this entire thing a capital E. Of course, you'd want to avoid using lowercase e anyway, because that might make people think it's the number e, which it's not. The table in the back of the book for the t distribution, if you wanted to use that to find the t value here. T distribution table, where is it? Okay, here it is. It's table 5. No, that's standard normal, excuse me. Table 6 starts on page 699, goes over a couple pages. There's gamma, that's the degrees of freedom. Go to 9 degrees of freedom. These numbers are areas to the left instead of areas to the right. So alpha is 0.05, so that alpha over 2 is 0.025, means we use 0.975. There's 2.262. Sorry. So let's use that now in the spreadsheet. We're still using the observed values of X bar from column L. Of course, the numbers are going to change again. So now I subtract 2.262 times not the 2.887 anymore, right? That was sigma. But instead, the observed value of the standard deviation, the STDEV. Don't put a P on it. Leave the P off. Still divide by square root of 10. Notice for this particular sample here that I haven't entered this yet, where the mean was 5.4776. The left endpoint, when we use sigma, was 2.887, is 3.688, but this left endpoint is 3.486, lower. Because the margin of error is bigger here, because 2.262 is bigger than 1.96. That's probably the main reason it's lower. The standard deviation could be smaller than 2.887. I'm not figuring it out here, I guess. Explicitly, I'm not showing it anywhere. Actually, maybe it would be good to see the standard deviation in each case on a separate column here. The different samples are going to give you different standard deviations. Their sample standard deviations. they're estimators for 2.887. Observe estimates, I should say. Although remember, S is not unbiased for sigma, right? S squared is unbiased for sigma squared. S itself, the standard deviation, sample standard deviation, is not unbiased for sigma, the population standard deviation, unfortunately. But guess we don't worry about it. Again, T is 2.262. I'm just going to use S from column P, divide by square root of 10. Huh, okay, there I'm getting a bigger number, 3.73 than 3.64. Even though 2.262 is bigger than 1.96, I guess, well, yeah, this S is less than 2.887, significantly enough to make this left endpoint not smaller than this one. I think usually it will be smaller. And in this case, it's smaller. Once I entered it, things changed. It's smaller than that. .262. There's my value of S divided by square root of 10. And things will change again. So again, column P is the S values. Based on those S values, we get a left endpoint and a right endpoint. Somebody email me right now, remind me to actually share this file with you. I don't want to go ahead and count how many of these contain or don't contain 5 anymore. Somebody could email me right now. I don't know why it's dividing by 0 there.
I think you used the right cell.
Did I?
Yeah, the A1 to J1.
Oh, thank you. Yeah. So used to going down columns instead of across rows. Okay. So it should be the case that around 5% of these intervals do not contain 5. About 95% of them should. I'm not going to go ahead and count them this time.